All right, so the last video that you have to watch, I'm going to make one additional one on 8.5. I've decided about graphing polar graphs. That's actually probably the coolest thing. So definitely want some bonus. Definitely make sure you watch that and kind of do the optional quiz that goes along with that section. But I will make it optional. But 8.4. So this section is about De Moivre's theorem. So we'll use a Frenchman in the 18th century, thereabouts. And this deals with raising a number that is in trigonometric form to some power. So De Moivre's theorem is dealing with if I have something like r cosine of theta plus I sine theta, and I raise that to, say, the power n. Okay. Well, what is that actually equal to? So his theorem states that it's actually equal to r to the n. So I raise r to the n power. And then I do something quirky with the n. So the n actually is going to get multiplied to the argument. So it's cosine of, say, n theta plus I sine of n theta. Okay. This may seem a little weird, but remember, if you have, like, let's say even, well, let me do it for the case of 2 with what we did last time. If I have the same complex number multiplied twice, I think it makes perfect sense from what we said last time about how I would multiply those two with the product theorem. Because according to the product theorem, I would do r times r, that would be r squared. And then I would do cosine of, say, theta plus theta. Before they were different angles, here they're the same, plus I sine of theta plus theta. So if I think about what that is, that's actually r squared cosine of 2 theta plus I sine of 2 theta. So you can see it for the case where we're squaring the number. So what I really just computed was r cosine of theta plus I sine theta quantity squared, and I wrote that out and multiplied it, and you can see that it is actually this. But what this theorem says is true for any positive integer power that I have. So if I cube it, fourth it to the 100th, extremely useful formula. And you can prove it by induction, which we're not going to do, but it's not a hard proof to do by mathematical induction. Okay, and what we want to do with this is, let's say, find the power. Number 1. So if I have something like 3 times the cosine of 30 degrees plus I times the sine of 30 degrees, and I cube it, we're asking what this is. So this is 3 to the third. And then by De Moivre's, it'd be cosine of 3 times 30 degrees. And then plus I times the sine of 3 times 30 degrees. And as before, we want to continue to go on to write that in rectangular form. So we are going to have 27 cosine of 90 degrees plus I sine of 90 degrees. And then we're going to have 27 cosine of 90 is 0, sine of 90 is 1. So you can see that really all we have is 27i. Okay, so not too bad. I mean, it would have been harder to go through if the number wasn't rectangular originally and then multiply it by itself 3 times in order to get that result. Whereas if we're in trig form. Then we can apply de Moivre's theorem, and boom shakalaka laka, we get the result, right? So let's take a look at another one. Maybe we'll do one where the angle's in radians, and we'll do to the fourth power. So say number 2. I've got 2 cosine of, let's say, 3 pi over 4 radians plus I sine of 3 pi over 4. And I'm raising that to the fourth power. Okay. So this would be 2 to the fourth, and then cosine of 4 times 3 pi over 4, plus I times the sine of 3 pi over 4, 4 times the 3 pi over 4. And this is going to be 2 to the fourth is 16. This is cosine of 3 pi plus I times the sine of 3 pi. Okay, so you might say, well, what's cosine of 3 pi? What's sine of 3 pi? Well, 3 pi is coterminal with pi, so if I just subtract 2 pi, cosine of 3 pi is really asking the same question as what's cosine of pi, because those are coterminal. They're going to have the same value. So cosine of pi is -1, so that means cosine of 3 pi is -1. Sine of 3 pi is the same as sine of pi. Sine of pi is 0, so the sine of 3 pi is 0. And I really get this result that this whole thing is really just -16. Okay. I want to also do something where I talk about how do I find square roots and cube roots of complex numbers. Now, this is something that you've had the same story for basically 12 years, and it was just part of the story. And today you're finally going to get the other part. Okay. Now, if I have something like this, and I say, find all the square roots of, say, 1, and I'm talking about complex numbers, including complex square roots, I really have x squared is equal to 1, and I really do get all of them if I just take the square root. There really are just 2, plus or minus 1. Right? But have you ever thought about like any other number? Like say I try to do that, and I say, what are the square roots? And let me choose some other number of, let's say, 4i. I would be thinking about the same thing. So I have x squared is equal to 4i. And if I take the same approach, could I really say plus or minus the square root of 4i? Well, that is a little bit of a no-no, because square root of I is mysterious. I mean, technically, I suppose I could state the answer like this, but I claim that there's a better way to write this out. And then, not only that, but it also solves the problem of being able to find cube roots and fourth roots and fifth roots. Like if I had said find all fifth roots, or let's say find all complex fifth roots, and I had said x to the fifth is equal to 1, and you'd said, well, take the fifth root as 1. Well, we've just gotten one of the 5. I missed the other 4. Now, how is that possible? Well, that's what we're going to talk about. Okay, so it actually has to do with this de Moivre's theorem and how we can go about and find all these square, cube, fifth roots of these complex numbers. See, one's a complex number. It's completely real, but it has other roots other than 1. It's just the fact that they're more mysterious as to what they are. Okay. So I'm going to start with this one. I'll show you how to do this over here. Find all square roots of 4i. The first thing you would need to do is you would need to write 4i in rectangular form. So you always write your complex number in rectangular form. So for the 4i, you really can see that if I just think about what 4i is, it would be right here. And the angle is just 90 degrees. Right? Or if we want the angle, and let's do it in radians, pi over 2 radians instead of 90 degrees. The book's using degrees, the Alex is using radians, so I'll use radians since that's what the Alex assignment is going to do, okay? And then if I want to write this, I also know that r is 4, and I can do that in one of two ways. Either 0 squared plus 4 squared is 4, or you can literally see it's just 4 away from the origin if I have 4i. And my x is 0. It's like 0 plus 4i. So r is 4, the angle is pi over 2. I can start by writing this complex number in polar form, so it would be like 4 cosine of pi over 2 plus I times the sine of pi over 2. Okay, now I want to solve for x. Now what I can't do is take the square root. That doesn't work very well for this. So instead what I do is kind of substitute the x. Instead of thinking about it as just a complex number, I substitute in the polar form. So the r cosine theta plus I sine theta. And that's squared. And what I want is for that to equal 4 times the cosine of pi over 2 plus I sine of pi over 2. And that's when we're going to use de Moivre's theorem. So by de Moivre's, this means that this left-hand side would be r squared cosine of 2 theta plus I sine of 2 theta. And that's got to equal 4 cosine of pi over 2 plus I times the sine of pi over 2. Okay. Now, so it's always going to be the same. I'll do a couple examples, but it looks bad, but it's not really. So all we do is we take the complex number. I write it in polar form on the right. I substitute in this complex number form, use de Moivre's theorem. I get to something like this. By looking at this, I can figure out the possible values for r, and I can figure out the possible values for theta. And once I know those two, then I supposedly get two different answers. Because if I'm talking about all the square roots of 4i, I should get two answers. Okay. So notice that in order for this to be true, r squared would have to be 4. So that really means that r is 2, not plus or minus 2, because r is only positive. So that represents the modulus, the distance. And then I also know that this angle has to equal pi over 2. So the 2 theta, that angle, has to equal pi over 2. But then here's the tricky part. So remember how cosine, the period is 2 pi. So it's really plus 2k pi. And k is some integer. And if I'm talking about square roots, that integer k can either be 0 or 1. So it starts at 0. And then if I'm doing a square root, it would go from 0 to 1. If I'm doing a cube root, k would be 0, 1, and 2. If I'm doing fourth root, k would be 0, 1, and 3. But in order to now find our different values of theta, I have to solve this for theta for these values of k. Okay. So if k is 0, for that value, I get 2 theta is equal to pi over 2. Multiply that by a half, and I see that theta equals pi over 4 is one value. For the other one, k is 1, And I would get this 2 theta is equal to pi over 2 plus 2, k is 1, so this is really just 2 pi. And then I would add these. So if I add those two, this would be 2 theta equals 5 pi over 2. 4 pi over 2 plus pi over 2 is 5 pi over 2. Multiply by half. Theta would be 5 pi over 4. Okay, and then I write out both my answers. So I know my r, I know my different angles. So my two square roots of 4i, what are those? Well, one's 2 cosine of pi over 4 plus I sine of pi over 4. So for an angle of 2 pi, or for an angle of pi over 4. And then the other one is 2 cosine of 5 pi over 2 plus I sine of 5 pi over 2. Okay. Now, typically, we would go ahead and write those in rectangular form, depending on what we want to do. So maybe I write these in rectangular form instead. And in that case, this first one would be root 2 over 2 plus I sine of root 2 over 2. Sorry, plus I root 2 over 2. So that's this first one, which would be root 2 plus I root 2. And the second one would be 5. What's the cosine of 5 pi over 2? Well, if you use a calculator for that, that should be 0, and this is just 1. So that is just going to be 2i. Let me just do this. Verify that in case you don't believe it. But sorry, I wrote, my theta was 5 pi over 4. I'm not sure why I wrote 5 pi over 2 here. Something was up. So this one in rectangular form should actually be, what is that going to be? Actually should be this, negative root 2 minus I root 2. Okay, so if you don't believe it, what I want you to do is take these two, which are fine, which is what I got from this process, and write those in rectangular. You should get this. I'm actually fine with this. I think that Alex makes you write it like this. So that would be kind of a check. Okay, that's finding the square roots. Let's do one where we're finding like cube roots or something like that. Okay. Let's do this. So this one says find all cube roots of negative 8i. Okay. So again, kind of the same idea. I start off with that same equation, only this time I want cube roots. So what complex number cubed is negative 8i? And I claim there's 3 complex numbers that do that. The next thing I would need to do is write the negative 8i in polar form, trigonometric form. So the negative 8i is down here, but I want this angle in radians, and the one that would be 3 pi over 2, right? And what's our r value? Well, it's square root of 0 squared plus negative 8 squared. I think you can see that's going to be 8. We're 8 units away from the origin there. So to get this one, I have this x cubed, and r was 8 My angle is 3 pi over 2. So I get this. And then remember what we do here. I plug in this polar form for this number. So it's r cosine of theta plus I sine theta, say cubed, is equal to this 8 cosine of 3 pi over 2 plus I sine of 3 pi over 2. So good so far. Parentheses here. And then by Demoivre's, this is going to be r cubed is cosine of, say, 3 theta plus I sine 3 theta. And that's equal to 8 cosine of 3 pi over 2 plus I sine of 3 pi over 2. Okay, now what? Well, I do the same thing that we kind of did in the last one. I need this r cubed to be 8. R cubed has to be 8, so really r is 2 if I take the cube root of 8. That's the positive number, the real number, modulus. So that is 2. And then I look at this, 3 theta. Well, that has to equal this 3 pi over 2. And then plus your 2k pi, right? But here, k, since I'm doing cube roots, I go 0, 1, and 2. So I go on up to 2. It's 1 less than 3, right? Where square roots was 1 less than 2, so I did 0 and 1 for k. So I'll let you verify this. I'm just going to write down mentally kind of what we're going to get. So if I do k is 0 and solve for theta, which you should check this, you should get pi over 2. If I do k is 1, should get 7 pi over 6. And if k is 2, I'll get 11 pi over 6. And that means my 3 complex numbers that do this are, my r was 2, so I have 2 cosine of pi over 2 plus I sine of pi over 2. I have 2 cosine of 7 pi over 6 plus I sine of 7 pi over 6. And I also have 2 cosine of 11 pi over 6 plus I sine of 11 pi over 6. So this is our answer. If we want these in rectangular form, which they might ask for, then we could also write this out as, let's see here. Well, let's just evaluate real quick. So cosine of 2, that's 2i. 2i. This one, negative root 3. Minus I. And then this one, root 3 minus root 3i. Okay. Ostensibly, those would be it. Let me just check those real quick for you. Make sure I made no errors. Actually, this one's just negative I. Okay. So either form is fine, either if you write it like that or you write it as the complex number here. If you actually cube this number, that would be one of the cube roots. So 2i is apparently one of them, one of the answers. So if I do 2i times 2i times 2i, that's 8i cubed. You may remember that I cubed was I squared is negative 1, so that's I cubed was negative I, right? Sounds right? So 8 times negative I, that's just negative 8i. So that's why 2i is one of the cube roots of negative 8i. And apparently these other two are if you go through and cube them as well. Okay. So maybe the last thing we should do is find all the fifth roots of 1. Should we do that? I think this is a cool place to end the course. And one last question. Or find all, let's state it this way, find all complex solutions to x to the fifth is equal to 1. That's actually kind of asking the same thing as find all of the fifth roots of 1. So you know one answer is 1, and you may have said, well, there aren't any others. There are actually 4 others. Let's talk about that. So if I look at the number 1, so that is out here. The angle I could think of as being 0. So it's either 0 or 2 pi, depending on how I choose my interval. Let's just say it's 0 here. And that means that r is 1, since it's square root of, actually, let's write this out in polar form here. So what is this? This 1 cosine of 0 degrees plus I sine of 0 degrees. So we're 1 unit away from the origin. So I'm talking about 1, that's like the 0.10 here. And our angle is 0. So that's if I write 1 in polar form. And you can see that this is the same thing, because cosine of 0 is 1, and sine of 0 is 0. So this is really just 1 times 1. It's really just 1. So that's what we want. And then I would substitute in the r cosine theta plus I sine theta. All that's being raised to the 5th power. Okay. De Moivre's theorem would be r to the 5th is equal to r to the 5th cosine of 5 theta plus I sine of 5 theta. And that's equal to 1 cosine of 0 degrees plus I sine of 0 degrees. Okay, and then I compare. Well, r to the 5th has to be 1. 5 theta has to equal to 0 degrees plus 2k pi. Here, though, since I'm doing fifth roots, k would go from 0 to what? 1, 2, 3, all the way up to 4, 1 less than 5. And then I would just go through and solve all these. Okay, now you can stop the video. I want you to go through and verify what we're going to get here. So that our answers to this, and I'll write them all in polar form. So the first one, so if I take the 5th root, r is 1, and really theta is equal to 0 if k is 0. Theta is equal to 2 pi over 5 if k is 1. Theta is 4 pi over 5. K is 2. Theta is 6 pi over 5, k is 3. And theta is 8 pi over 5 if k is 4. Okay. And then r is 1 on all of those. So if I write out all of the actually complex roots to that, all the solutions to this equation, it would be 1 cosine of 0 degrees, so for this first angle, plus I sine of 0 degrees. That's really just 1, so that's like the number 1 that you would have guessed, right? But then you got these other 4, so cosine of 2 pi over 5 plus I sine of 2 pi over 5. And just listing these other ones. So I've got the number 1, and I've got these other really weird 4 different angles here with radians, complex numbers. Any of these numbers, if I raise them to the 5th power, I'm going to get 1. Okay, so that's it. I got a video to do on that. And then I'm also going to post one about graphing and polar equations.